So, very good evening, everyone. And now I'm resuming the discussions of the previous class, which we have talked about merge sort analysis. And I requested everybody to implement merge sort before we start with the discussions. As I told last time, that we are going to do today quick sort. Quick sort analysis is primarily what will be the focus of today's class. But before that, we already said that read the Horace quicksort also, although we are not going to, for the time being, touch upon that. But I would like to know, are you aware of how Horace quicksort version differs with the Corman's quicksort? And the Corman books version is what we are going to look at. So I will start with this version first, and then have some discussion later how it is different than Horace's original quicksort version. So as you know, quicksort, primarily the logic in this case is also a recursive and a divide and conquer based. But in this case, it says that choose a pivot. So general quicksort says choose a pivot element. Pivot means any key, any special element which you will take to a good position, any main element, any special value. So anyone can be chosen as a pivot element and put it at its correct position. So we have to find out its correct position at its correct position. That is the first step of your programming in this direction. Correct position in the array. Say if you have array ARR, so I would like to place it at the correct position. Then what does correct position mean? That all values on the left of pivot are less than or equal to the pivot element. They will be less than or equal to pivot element. And all values on the right, all values will be greater than or equal to pivot element. That obviously becomes its correct position. And that will mean that whatever sorting you do, once you have some value at the correct position on the left side, that can be individually sorted, right side can be individually sorted. For example, if I say I have 25, 30, 15, 17, 45, etc., etc. So let's write here more clearly. Say I have 25, 30, 15, 17, 45, 55, and let's say this is my pivot. Then I will say I should do in a way that 25 reaches to correct position. If the total values are 1, 2, 3, 4, 5, 6, 7, say let's take another value 8, 18. So I have total 8 values. Out of this, if I say 25, then 17, 5, 18, 15, these 4 values will be before 25. So that means some 4 values will come here. In what order doesn't matter, but guaranteedly 25 is supposed to be here, and this side other remaining values. In what order? No idea, but ultimately I want my 45, 50, and 30 to be this side in any order, and this side I want values 15, 17, 18, 5 in any order, but they will be on the left of this 25, and other values which are greater than 25 will be on the right of 25. Then 25 is its correct position. So if I am able to find correct position for 25, my next step will be that I have to quick sort again left sublist and right sublist. That's it. So more or less, you can say quick sort list, quick sort left sublist and right sublist. That straight away makes the recursion visible in the recursion of a quick sort, or in the designing the solution for quick sort, the same word coming again. So recursion becomes visible. Another condition for recursion is size must reduce. So that also we can see that size of each call will ultimately be lesser than the previous call. Guaranteedly, sublist cannot have more than n minus 1 elements because pivot is not in this. So even if the size was n, left sublist will be at most n minus 1, means some size reduced. Similarly, right sublist at most n minus 1 is possible, size is reduced. And third condition for recursion to say is recursion must stop also somewhere. So primarily, recursive solution will be always feasible if you are able to make a recursive definition. So the solution of the problem must have a recursive definition of the solution. First issue. Second is the size must reduce. And the third is the recursion must stop sometimes. Yeah, this should not be infinite. Non-recursive step must exist. Non-recursive point must come. Obviously, I can say if the list has a 0 element, or if the list has only 1 element, recursion will be stopped. So if I can say if n is less than or equal to 1, I can easily say recursion will stop ultimately. So using this concept, let's go for understanding how quicksort can be implemented. So knowing this, now I can easily see, again, as we have already discussed, so we will require recursion to be used. So start and end both will be needed. Then the question is finding position for the pivot is going to be most important. And who will be pivot? That is another question to be answered. Rest steps are self-explanatory, nothing big to be done. So first, who will be the pivot? Well, Hore's quicksort. So Hore's quicksort said that first element is taken as pivot. That is, I'll say array 0 initially is taken as a pivot. But Corman's version, the version which we are current discussions going on, here last element is taken as pivot. Means effectively array n minus 1 for the initial call. Of course, recursive calls will have accordingly n reduced, and accordingly that will be the position, or end position. You could say array end will be the pivot. In this case, to be precise, we will say array start will be the pivot. Because sometimes we could be, we're starting with non-zero, sometimes we could be ending with non-n minus 1. So this is a better precise answer to say this. Second, so this is one difference. Second difference, how to find a position. So in case of a Hore's quicksort, if you have list available as, let's say 25, 40, 30, 11, 7, 9, 5, and let's say if I have value, let's say 8. So what we will say is correspondingly, if let's say anyone is pivot, in case of a Hore's quicksort, I started from this direction, J started from this direction, and we will keep on finding some mid position for pivot. Let's say this, I take a slightly, this value I make it as, let's say 18, and make it as say 27. So we will have a few values before 18, few values after 18. Somewhere mid, I expect to have, say, pivot. And before pivot, all values are less than, if equality is also there, then less than equal to values on the left side. And all values are greater than pivot or even equal to also could be there. So they could be coming on the right side. So whenever you get any value which is a bigger than pivot in the I side, or any value which is smaller than pivot in the left side, then they are swapped with each other. This is how Horace quicksort works. And accordingly, things will progress. On the other hand, in Corman's quicksort, it is not done like this. So Corman's quicksort version effectively works slightly different. It says you have the values. So I say from start to I minus 1 is, or I'll say start to I is list of values less than equal to pivot. At all times, I should be such that all values which are less than equal to pivot, they will be in the initial part. So I will say as soon and from first element, or I will say from start, or J will move one by one. J will progress from left to right one by one. And if AJ or if array J is less than or equal to pivot, I will say append this into I list. I list, I have used the word. I list means the list of the values which are on the left of pivot, and all values which are less than or equal to, they will be considered the I list. So I say there is a I list which is having all values on this side, and I am going to append this. It will be more clear once I take some data. So let's assume we talk of the previous data itself, 25, 40, 30, 11. So I say I have values 25, 40, 30, 11, 17. Let's take 27, 9, 5, 27. So this is 27, 9, 5, 80. So initially my I list is empty. So this is element 0. This is element 7. So I will say pivot is nothing but array 7. That is value 18. So this is pivot 18. So my J will start from 0 to n minus 1, because pivot is nth element. So I will say it will go 0 to n minus 2. And I will keep on finding. First of all, I say 25. So array J. If array J is 25, so currently it is 25. Is it less than equal to 18? No. Go ahead. J progresses. So J becomes 1. Next time I go. Now 40 less than equal to 18? No. 30 less than equal to 18? No. Nothing to be done. And then comes 11. 11 is less than equal to 18. Means append 11 into I list. So my initially I list is empty. I list is always on the left side. So immediate first position is going to be appended. So append into I list will mean I equal to I plus 1, and A double R I should get 11. But say if I say first time, so I will say I was initially out of range. I should become 0. I want ARR0. Initially, I will be incremented and I list has to start. The first value which at I list should to go is array zeros place. So I should get 11 here. But if I put 11 here, 25 will be lost. So effectively what I will do is when 11 is coming here, I will swap these two values. And I will say, so swapping will mean this becomes 11. You have here 40. You have here 30. 25 comes here. I is here now. J was already here. And we have the next value 27, 9, 5, 8. This is already done. So after this, I will next have J incremented. J comes here. 27 still greater than pivot, nothing to be done. Equality I am not taking for the time being, but later we will discuss. Comes to 9. 9 is less than 18. That means 9 is supposed to be appended into the I list. So this will mean this and this will be swapped. This means this will become 9 here by I coming to this place. This will become 40 here. And now J will be incremented. J comes to next position, 5. 5 is again less than pivot. 5 again to be appended into I list means I further shifted. I comes here. I comes here means this versus this to be swapped. So I will have here this value going as 5, this becoming as 30, and now list over, J is over. So effectively my position for 18 will be next to I. I is up to this is I list. I say this is my I list. Next to I position is guaranteedly for the pivot to come. And I can easily see pivot will come here. That will mean this and this value will be swapped. And once it comes here, 18, this will be 25 here. I can easily see values on the right of pivot are already greater than, or I'll say the values are now greater than the pivot values. So this becomes the overall logic of quicksort versions implementation. And say, having said that, so I can definitely now say go further and discuss further. So now we can do the coding part of this. As we have already discussed, things are very easy, nothing difficult. Void quicksort. Of course, ARR to be needed. Start and end both will be needed instead of simply end, simply size, because you know that recursion calls with non-zero starting index also needed. So we will have this. First is we have to know the pivot and find its position. So I will say this step is always called as partition step, and we always say position equal to partition. Now, who will be taken as a pivot, how it will be found out, that all can be a part of partition logic. So partition logic obviously needs an array, and partition also needs the start and end parameters. So based on that, we will find out, and the position on which pivot is supposed to come or pivot has come, that will be returned. So in this case, like we said, 18 reaches to position. So if I say 18 was supposed to be having 4 values on the right, so 18 will reach to index 4. So position will be 4. 0, 1, 2, 3 will be other values. 0, 1, 2, and if there are any more values, so there are only 3 values, 5 in. So this will be position will be 3. I think we have taken 7 values earlier, or yeah, 1, 2, 3, 4, 5. So I have 5, 9, and 11 to be this side, and all other values, 4 values coming on the other side. So 18 will come at index 3, position 3. So position will be coming where the pivot will be placed. Once pivot is placed at that position, left sublist to be quick sorted. Left sublist to be quick sorted means I have to call quick sort with the start to ending position. Ending position is POSN, not POSN, to be precise, POSN minus 1. Because at position, pivot has come. Pivot need not be sorted again. Pivot is at right place. Size has to be reduced. So pivot is never to be considered again. So the one call will come with up to pivot minus 1 position. And the second call will start with pivots plus position. So that is position plus 1 from there up to end. And once it is done, nothing else to be done. So effectively, if you say this is a divide step, this is a conquer step, and no combining needed explicitly. So combine is simple, nothing to be done. But in this case, divide is more complex. In case of a merge sort, divide was a simple, merge combine was complex, or combine needed extra logic or loop. Here divide needs extra logic or loop. Then comes, let's write the partition as it is supposed to return a data type. So I will have int partition. Now in this case, all parameters. First thing will be choose a pivot. So as we discussed, pivot will be ARR end. Last value. Initially, I list is empty. So I is always before the first position, that is a start position. As I list is empty, so I has to be start. But if I write I equal to start, it will mean first value is up to I. That will be incorrect. So ideally, I will say I equal to start minus 1. For example, if I am saying initially I have 25 and other values like just we saw, initially we had 25, 40, 30. So I is here initially, means effectively minus 1 if a start was 0. If a start was some other value, accordingly this. So initially I is here, and then I'm going to start with the all elements to be compared from. So J is going to start with the start. J is going to end somewhere where I have to see up to what. Of course, pivot is already there, so I have to decide where to go, and every time J to be incremented. Then what I have to do? Ultimately, I have to have some condition such that if the condition is true, I would like to swap A, or before swap, I will say first I equal to I plus 1, and then I will say swap ARRI with whom? With ARRJ, because that element is supposed to come here. And that condition now I have to see. So what should be the condition? Obviously, this condition is array J versus the pivot. So if I say array J versus pivot, if array J is greater than pivot, it is not to be touched. If the array J is less than or equal to pivot, I say this is supposed to go to I list. So effectively, this whole logic is go to or append to I list. Append element to I list. And I list means I to be incremented and then swap so that nothing is lost. This process will be repeated, and all values which are less than or equal to pivot will reach into the I list. So effectively, now I have to decide that what should be the index here to put the pivot element. At which position? That position will be the, with respect to I have to think definitely. So you can easily think what it should be, and then accordingly the same position to be returned also. So effectively, this as well as this, both of these are with respect to I have to see what is this. So to be precise, you can easily think this should be I plus 1, not simply I, because up to I the values are less than or equal to, and next position for the pivot is guaranteedly suitable. So you can think of doing something like this. This is what becomes quick sort logic we can easily understand. Going beyond, now we can just quickly see that what we have discussed. Once again, we found the position by having the partition logic called, which is a divide step. Then recursively we solved both sublists, no merging or no combining extra needed. How did we partition? We chose the last element as a pivot. ith list is to be appended every time. So I is initially start -1. Whenever an element is to be added to I will increment I and bring the correct value into this. And swapping will be needed so that no value is lost from the position where I is appended. All elements from start onwards up to some point are needed to be checked one by one. Every time I will check the array J value with the pivot value, and pivot value, if it is array J is if less than or equal to, it should be going to ith list. Otherwise, it is not to be disturbed. So all values will go into the ith list like this. So having said that, maybe let's take some more other example where we will have the same partition to be done. Let's say I have value again 25, 30, 40, 45, 30 once again, 25 once again, and let's say I have some value 70 and the pivot is 35. Now intentionally I have taken a different kind of a value. So initially my I is here and this is my J. I find 35 versus 25. 25 supposed to go to ith list. Ith list is empty. I will be incremented. I comes to same position. 25 will be swapped with itself. I is also here. J is also here. Both will swap with each other. So still 25 will remain here. I reaches to this position, but J shifts next time to this. Now J is 30. Again, 30 is less than 35. So again, I will be incremented. I comes here. Array I and array J will be swapped. So again, this will come here. And then again, a swapping with itself will happen. Still perfect. Then J becomes incremented. J comes to this position. J becomes 40. Or array J becomes 40. 40 versus 35, not to be copied. J further shifts to this position, not to be copied. J comes to this position, 35, 30 again. Now this 30 needs to go to I list. I was up to here, so I will be incremented. I will come to this position. This position will mean now this and this value will be swapped. So this 30 will come here and this 40 will go here, and this way we are able to swap. So 45 remained here correctly, 40 this and like this. So by this example, you can see that sometimes the swap will mean copying into itself or same value to be swapped with itself. Well, doesn't matter, but in this case, you can easily understand this works easily without a difficulty now. So once done this, then we have to do the analysis part. Analysis, not difficult, not very difficult, simple. If I say T of n to be done, I have divide step plus conquer step plus combine step. Divide. In this case, divide means partition. This is going to be order of n. I can easily see the previous logic. Loop exactly n time works here. So I can guaranteedly say it is order of n. Order of n, to be precise, I will say it is a theta of n. Theta means exactly in terms of n. Big O means upper bound. You are aware. So theta is exact bound. Of course, in next class, we will discuss what is theta versus O. But theta is a better notation and should be used more appropriately whenever it is fully applicable. So in this case, the steps will not be less than n in any time. It will be exactly n steps. So I can say it is exactly theta of n. And combine conquer step. Conquer step means 2 recursive calls, but whether recursive calls will be with the same size or not, that is not sure now. And combine is effectively order of 1, so nothing special to be done. So I can say this is going to be theta of n plus 2 recursive calls. 2 recursive calls will mean t of something, or this may be some factor also. How it will be decided. In case of a merge sort, the recursive calls were guaranteedly 2. A was guaranteedly 2. Size was also always n by 2. So in case of a merge sort, we could easily say 2t n by 2 as a conquer step. But in this situation, this is not guaranteed. Conquer step is not fixed. Conquer step size not fixed. Why not fixed? Because we are not sure where my pivot will reach to. My pivot might reach to exactly middle, might be in the middle, but might not be also at mid, and might be at some extreme border, extreme boundary. So now I cannot say that I can directly write. When such comes the situation, this leads to again 3 different cases that I will think of a best case, I will think of worst case, I will think of average case, as we have already done for the insertion sort also in the similar manner. Best case. Best case will mean my conquer should be best. Conquer best will mean that my both calls should be with the smallest possible size. Smallest possible size for both cases can be n by 2. That will mean the pivot must come at the mid always. Pivot must reach at mid always. At mid in every call, in every recursion. So if it is so, then I can easily say, if it is so, then my Tn will be theta of n for the divide plus 2 calls, each call with approximately n by 2, because actually it is n minus 1 elements remaining. Pivot has come to the position. So ideally, I can say it will be n minus 1 by 2 in the left sublist, and ideally maybe approximately n minus 1 by 2 on the right sublist, because n could be odd or even. So approximately I can say, doesn't matter with minus 1 or so, but both sublist will be exactly half. This will become best case. Again, to be solved, without going into much detail or without going into more complicated analysis, I can solve it slowly, and probably we will get it as theta of n log n. For merge sort also we will get this. For quick sort also we will get. How? We will see, we will solve. But we can remember that, yes, it will come like this. But go for other case, worst case. So in case of a corresponding quick sort, worst case should mean that I should have less use of recursion, or worst situation should come. Worst situation will mean one sublist is empty and other sublist is maximum size. And other is of maximum size. So my divide and conquer didn't help much, and I got not equal division lists. I got one sublist to be empty and other to be of maximum size. What does that mean? Let's assume that your pivot reached to either at the start or at the end. At start or at end. Now, in that case, obviously, you can see one sublist will be empty. And that will be the worst case. When this will happen, now you can easily see if list was sorted, last element is the pivot, and that will still continue to the end. So that will be making this situation. List was reverse sorted. Last value was the smallest. After bringing the pivot to the right position, it will reach to the start. That will mean left sublist will be empty and right sublist will be of the full size. So this will mean T of n will be equal to theta of n, obviously, plus what? One call with a zero size effectively means forget about this, plus second call will be with size n minus 1. So instead of n by b, it becomes n minus 1 because pivot has reached to position, correct position, except pivot, every element will be in the second list. So effectively, this will become T of n equal to theta of n plus T of n minus 1. Ideally, this is solvable without much complex mathematics. T of n minus 1, just substitute the same definition. It will mean theta n minus 1 plus T of n minus 2. Substitute this again, theta of n minus 2 plus T of n minus 3. And so. Ultimately, you will reach to T of 1. T of 1 means n equal to 1. N equal to 1 means no recursion. This is order of 1. So effectively, this will become equal to some steps in terms of n plus some steps in terms of n minus 1. Theta n primarily means n steps. Theta n minus 1 means primarily n minus 2 steps plus n minus 3 steps plus n minus 2 steps and minus 3 steps up to 1. You can say effectively it will be called as big O of n scale. So worst case of quick sort is going to be order of n scale. On the other hand, just imagine what was the worst case in merge sort. In worst case also, or in best case also, irrespective of any data properties, my lists are always balanced. Irrespective of data, each list is of n by 2 size always. So in case of a merge sort, best case, worst case, average case, all will have same relation Tn equal to theta of 1 plus 2Tn by 2 plus theta of n of the merging step. Ultimately solves to effectively theta of n log n. Whether you say theta of n log n or you say n of order of n log n, more or less the same thing for the time being, and you could say anything like this. But in quicksort, worst case we have already seen, and what about average case? So average case means assume that not the best case happen, not the worst case happen. So in quicksort, I will say in quicksort, one list gets, I'll say first list gets, let's say on average n by 10 elements. Second list gets 9 n by 10 elements. Highly imbalanced, but still in terms of n. So I say if I say that 1/10 element go in one list, 9/10 element go in other list, or you could say 1/3 go in one list, 2/3 go in other list. So average case will mean not the best n/2 n/2. So to be very taking a realistic picture, say even if n is say 10 lakh, if I assume only 10% elements go in one list, 9-10% go in other list, that also can be considered as an average case. But that will mean Tn will be equal to the dividing time, that is partition time. So that was a theta of n, plus first sublist to be called with the size n/10, and a second list to be called as T9 n/10. So we have to solve it. We will understand how to solve, but ultimately whatever answer we will get, that will be the analysis for the quick sort. Having said that, I think it has made things very clear to you. Let's quickly stop here. And why I am stopping here is that now we are going to see some of the code related to merge sort for those who are not good in programming. And then we are going to see partial code for Corman's quick sort version. But before that, let's see merge sort implementation. So as we discussed last time, that first of all, we will calculate the n1 number size first, n2 second. Then I am going to declare the corresponding L as this extra element, R also with an extra element. This is a merge logic. Let me show you the merge sort logic initially. It will be simple. Merge sort, find out mid, but mid is to be found by considering the condition. If it cannot be anytime unconditional, ideally I should always do the module, the indented programming. So I think by some mistake this has been removed. I have corrected that. Let me save it first. And now, so I say find mid, call merge sort for the first list, call merge sort for the second list, and then you have to merge ultimately. So this is the merge code. Now let's see the merge logic. Quickly we can see I declared L1 and R as right array, first list being copied. So you can easily see either I start with 0 to less than n1, or I start to mid 1 and the same thing. You can also write here, say I equal to maybe start to mid, and then accordingly in L, you could have like this. For example, I could write it as I less than equal to mid, I plus plus, and then I could say here, it should be taken as LK plus plus, and I could take a K as a 0 initially. So I can do like this also. It is one and the same thing. And this side I will have array I. So like this also I can write, or the previous way also I could write. Similarly here, I could do this mid plus 1 onwards, either start with mid plus 1 to end, or do like this. Then I said nothing but Li to be equal to int max, Li because effectively 0 to n1 minus 1 values are copied. So at n1 position, automatically, now instead of I will say here Lk. You should write not I, because I has been used in a different way. So Lk, K has been already incremented. Here R I have not changed. So Rj equal to int max. Then I will start with I as a 0, J as a 0, and K will go start to end as we wrote. Comparison to be done. Now I say, what if less than equal to is replaced by less than? Will it be correct or not? You have to answer this and find out. So array K equal to Li plus plus, otherwise array K equal to Rj plus plus. So that's it, simple logic. Then whatever quick sort just now we discussed, showing you code. Those who want to practice of their own, they can write their own code. But if you want, or they can pause this video and do your own. And otherwise, you can definitely have a look on this. If you are poor in programming, this will help you in understanding what you have to do. So for merge sort also, let me show the main also. How do you call main? So maybe you will declare array n, scanf n, read the values. Again, in this case, there must have been the indentation. Merge sort will be called merge sort with the start as a 0, end as n-1. And then sorting will be printed by using something like this. So this way, this becomes 1. Similarly, for the Corman, for the quicksort implementation, more or less we have the similar logic. First of all, in this, I have this. Instead of merge sort, the call is quicksort. Rest all main remains similar. Then how to write quicksort? Quicksort, obviously, I will have some condition. If my pivot is, if I have the value of number of elements as greater than 1, only then the recursion is to be done. So I will find out the position or pivot location by calling partition. Quicksort to be called, quicksort to be called. And then how partition will be written, parameters you know. Then I will say, if the partition is to be done based on the condition only, I will do. If I rewrite the condition, good enough. If I don't write, still it will work correctly. So it's not compulsory that I need to write this. I can remove this also, because automatically that will be taken care at the previous level also. So it's your choice whether you write or not. Pivot is, I will say, ARR end. Or if I am in this code, I am writing effectively pivot index effectively. So this is pivot index I am using. And if pivot index is taken, I is taken start -1, j from somewhere to somewhere, and I compare with pivot index. Because either you write pivot itself or you write array pivot index. Then you will be swapping or doing something. Ultimately, then at this point, you have to put pivot at right position. So I will say here the code will be put pivot element at the right position, pivot value, not index, at the correct position. And that position is ultimately related to I, and then that will be returned from there. So your choice, whether you write here, say we just said that in partition, we have compared it with the pivot index, or you can directly have, say, I can say you will have ARRJ, say less than equal to pivot value. And accordingly, you can accordingly have the pivot value used. So either you use index and then you will require a bracket and index scare brackets to be used, or otherwise you can do it like this also, and then accordingly you can write the simple code in that particular way. So it's your choice the way you want to do it. So with this, I think I'll stop, and now we can have the implementation stop. You must do the implementation at your level, and then you will be able to appreciate and do coding in a better manner. Bye-bye, all the best.